An Enigma machine is any of a family of related electromechanical rotor machines used for the encryption and decryption of secret messages. This model and its variants were used commercially from the early 1920s, and adopted by military and government services of several countries, most notably by Nazi Germany before and during World War II. Like other rotor machines, the Enigma machine is a combination of mechanical and electrical subsystems. The mechanical subsystem consists of a keyboard, a set of rotating discs called rotors arranged adjacently along a spindle, and one of various stepping components to turn one or more of the rotors with each key press. The continual movement of the rotors results in a different cryptographic substitution after each key press. The mechanical parts act in such a way as to form a varying electrical circuit. The actual letter substitution is indicated electrically. When a key is pressed, the circuit is completed. Current flows through the various components in their current configuration and ultimately lights one of the display lamps, indicating the output letter. The rotors, alternatively wheels or drums, Walzen in German, form the heart of an Enigma machine. Each rotor was a disc approximately 10 cm in diameter made from hard rubber or bakelite with brass spring-loaded pins on one face arranged in a circle. On the other side are a corresponding number of circular electrical contacts. The pins and contacts represent the alphabet, typically the 26 letters A, Z. This will be assumed for the rest of this description. When the rotors were mounted side by side on the spindle, the pins of one rotor rest against the contacts of the neighboring rotor, forming an electrical connection. Inside the body of the rotor, 26 wires connected each pin on one side to a contact on the other in a complex pattern. Most of the rotors were identified by Roman numerals, and each issued copy of rotor out was wired identically to all others. The same was true of the special thin beta and gamma rotors used in the M4 naval variant. The Enigma's complexity and cryptographic security came from using several rotors in series, usually 3 or 4, and the regular stepping movement of the rotors, thus implementing a polyalphabetic substitution cipher. When placed in an Enigma, each rotor can be set to one of 26 possible positions. When inserted, it can be turned by a hand using the grooved fingerwheel which protrudes from the internal Enigma cover when closed, so that the operator can know the rotor's position. Each had an alphabet tire, or letter ring, attached to the outside of the rotor disc, with 26 characters, typically letters. One of these could be seen through the window, thus indicating the rotational position of the rotor. The naval version of the Wehrmacht Enigma had always been issued with more rotors than the other services, at first 6, then 7, and finally 8. The additional rotors were marked Vi, 7 and 8, all with different wiring, and had 2 notches cut into them resulting in a more frequent turnover. The 4-rotor naval Enigma M4 machine accommodated an extra rotor in the same space as the 3-rotor version. This was accomplished by replacing the original reflector with a thinner one and by adding a special, also thin, 4th rotor. That 4th rotor was one of 2 types, beta or gamma, and never stepped, but it could be manually set to any of its 26 possible positions, one of which made the machine perform identically to the 3-rotor machine. The Kriegsmarine procedures on sending messages with the Enigma were complex and elaborate. Prior to encryption with the Enigma, the message was encoded using the Kurzsignalheft code book. The Kurzsignalheft contained tables to convert sentences into 4-letter groups. A great many choices were included, e.g. logistic matters such as refueling and rendezvous with supply ships, positions in grid lists, harbor names, countries, weapons, weather conditions, enemy positions and ships, date and timetables. Another code book contained the Kennengruppen and Sprachschlüssel, the key identification and message key. The Colossus computers were used in the cryptanalysis of high-level German communications, messages which had been encrypted using an Enigma cipher machine. Part of the operation of Colossus was to emulate the machine electronically. To encrypt a message with the machine, the plaintext was combined with a stream of key bits, grouped in 5s. The key stream was generated using 12 pinwheels, 5 were turned by the British G wheels, another 5 psi wheels, and the remaining 2 the motor wheels. The wheels stepped regularly with each letter that was encrypted, while the wheels stepped irregularly, controlled by the motor wheels. The first task was wheel breaking, which was discovering the pin patterns for all the wheels. These patterns were set up once on machine and then used for a fixed period of time and for a number of different messages. The second task was wheel setting, which could be attempted once the pin patterns were known. Each message encrypted was enciphered at a different start position for the wheels. The process of wheel setting found the start position for a message. Initially Colossus was used to help with wheel setting, but later it was found it could also be adapted to the process of wheel breaking as well. Colossus included the first ever use of shift registers and systolic arrays, enabling 5 simultaneous tests, each involving up to 100 Boolean calculations, on each of the 5 channels on the punched tape. Although in normal operation only 1 or 2 channels were examined in any run. Colossus used state-of-the-art vacuum tubes, thermionic valves, teratrons, and photomultipliers to optically read a paper tape and then applied a programmable logical function to every character, counting how often this function returned true. Although machines with many valves were known to have high failure rates, it was recognized that valve failures occurred most frequently with the current surge when powering up, so the Colossus machines, once turned on, were never powered down.